Okay, so if we have the limit as x approaches 0 from the right of 2 over tangent of x minus 7 over x squared. If you remember your graph of tangent x, kind of looks like that. So as you're approaching 0, this number is getting smaller and smaller and smaller. So 2 divided by a really, really small number. Oh, maybe should have moved that over a little bit. So that's going to equal infinity. So it's just getting closer and closer to 0. Minus, if you have 7 divided by a really big number, so if you have 7 divided by a million, then 7 divided by a billion, then 7 divided by a trillion, it's going to get smaller and smaller and smaller and smaller and smaller. So now you have this value that's basically getting bigger and bigger and bigger and bigger and bigger. Okay, so this, approaching 0, what I said infinity, approaching 0, then as it's getting smaller and smaller and smaller, this is getting closer and closer to infinity. I think I said it the other way around. Okay, so now you have infinity minus infinity, which is not indeterminate. So we can't use L'Hopital's rule.
When we're plugging in values in this direct substitution portion of the equation, when you have a constant over a variable, you're plugging in these numbers, why are we saying that that's infinity? Shouldn't it be like 1 over infinity? Shouldn't it be 0 because you're getting smaller and smaller and smaller?
Oh, this one you're approaching 0.
Right.
So really, if you divide 7 by, and always use the 0.1, 0.01, 0.001. If you divide it by 0.1, then you have 70. And if you divide it by 0.01, you have 700. And 0.001, 7,000. So the smaller your denominator gets, the bigger the entire thing gets.
And that's the case for both?
Yeah.
Okay, thank you.
No problem. All right. So since we can't use L'Hopital's rule, we just have to manipulate this a little bit. Okay. So if we have our limit as x approaches 0, and give it a little bit of space, so 2 over tangent x minus 7 over x squared. You can multiply this one by x squared over x squared. Multiply this one by tangent of x over tangent of x. Okay, so that will give us the limit as x approaches 0 of...
Isn't it from the right?
Oh, yep, from the right.
Oh.
Yep. Okay, so 2x squared minus 7 times tangent of x over x squared times tangent x. Okay, so we know that limit of tangent of x, as it's getting closer and closer to 0 from the right, is actually equal to 0. So you have 7 times 0 and 2 times 0, which is just 0. And here, if you plug in 0, 0 times anything is just going to be 0. So we have our indeterminate form. Which means we can use L'Hopital's rule. Okay, so we have the limit as x approaches 0 from the right of the derivative of 2x squared minus 7 tangent of x divided by the derivative of x squared tangent x. Okay, so that's going to equal, move that up some. The limit as x approaches 0 from the right gives you 4x minus 7 times secant squared x. Divided by, here we're going to have to use the product rule. So you have x squared times secant square root of x minus 2x times tangent of x. Okay, so again, through direct substitution, if we plug in 0, we have 4 times 0, which is 0. And we know that secant squared of x, we can make that secant x squared, which is just 1 over cosine of x squared. So if we plug in 0, that's just 1 over cosine of 0 squared, which is just 1 over 1 squared, which is 1. So this is just negative 7 times 1.
When you do the product rule in the equation on the in the denominator, shouldn't it be x squared secant squared x plus 2x tan x?
Oh, plus. Yep, thank you.
Okay.
Yep, I just think looking up at the top, got my minus there.
You're good.
All right.
I just wanted to make sure I was getting that.
So here you end up with negative 7. Okay. But in your denominator, once you plug in 0, you have x here and x here, you just get 0. So the limit as x approaches 0 to the right is equal to 0. Now the limit is equal to 0. It's not actually 0. It's just getting closer and closer and closer, and it's reaching 0. So this is just getting smaller and smaller and smaller. So if you have negative 7 times some really, really big number, so really you end up with negative, I'll just put that out to the front, kind of the limit as x approaches 0 to the right. Okay, so here you just have a really, really big number that's getting bigger and bigger and bigger as it's getting, the denominator is getting smaller and smaller and smaller. So you have negative 7, it's negative 7 times some infinite number. So if you have some infinite number times a negative number, it's just going to be negative of that infinite number. So it's negative infinity. Yes.
If you wrote the tangent in like a different way, like sine over cosine of x, would you even have to do half the stuff that we did? Or would it still be, like, if you put sine over cosine, would that be indeterminate before we even proceeded? Does that make sense what I'm trying to ask?
I think so. You mean if you did it maybe like up here or up here?
Yeah.
We can see.
If it was 2 over sine over cosine.
Oh, we can see. It's possible. So let's say if we did write it like that. So if we have 2 over tangent of x, if we made that 2 over sine of x over cosine of x, which would
2 cosine x over sine.
Yeah, which would be 2 cosine of x over sine of x. So if we plugged in 0, that would give us 2 over 0, which wouldn't be indeterminate.
Okay.
Yep, so that one actually wouldn't work. So the limit 2 cosine of x over sine of x as x approaches 0 from the right would just be 2 times 1 over 0. Yep, so that one still wouldn't work. But sometimes little things like that will work, so.
Yeah.
Oops, sorry about that.
Is it worth like going that way to like rewriting equations like that, or no?
If it only takes a couple of seconds and it might save you a lot of work, then I'd try it.
I guess it could
Yeah.
also make more work.
Yeah, and that's if you see it's making more work, then yeah, I'd cut it off. But Sometimes if it's something like that and it'll just take a few seconds to check, I'd go ahead and check it.
Okay.
All right. Any other questions on this one? All right. Bring it back up here for a minute. All right, so we'll do one more example. Oh, let's leave that up there a little bit. Make sure we get that. All right. Okay, so let's say, for example, we want to find the limit of sine of x to the power of x as x approaches 0 from the right. Okay, so we know as x approaches 0 from the right, sine of x to the power of x. If we plug in 0, we get sine of 0, which is 0 to the power of 0, which is not indeterminate. So we can't use L'Hopital's rule. Okay, so we have to manipulate this one, and these are a little bit trickier to manipulate. So we let y equals the limit of sine of x to the power of x. Okay. And we apply the natural log to both sides. Okay, so that means we have the natural log of y equals the natural log of the limit of sine of x to the power of x. Yeah. I'll make that a parentheses just to match it. Okay. Now this is continuous. We know that sine is continuous everywhere. So that means that the limit, well, the natural log of the limit is equal to the limit of a natural log. So you can actually swap those two out. Okay, so you have your natural log of y is equal to the limit of the natural log of sine of x to the power of x. Oh, as x approaches 0 from the right. Forgot to write it here too. Okay, so we know just using our natural log property that x can come down to the front. Equals the limit as x approaches 0 from the right of x natural log sine of x. Okay, now this, we know if we plug in 0, we can't have natural log of 0. So since, where's natural log, yep, that would just give us 0 times natural log of 0 is infinity, because that's, because that's getting smaller and smaller. It's not actually 0, so it's just getting smaller and smaller. Okay, so you have the, what was I getting ready to write? X equals 1 over x. can actually rewrite it that way. It gives us a natural log of y equals the limit as x approaches 0 from the right of the natural log sine of x. About the natural log over 1 over x. So we know as this gets closer and closer and closer and closer to 0, your sine of x, which we know that graph kind of looks like that, that gets closer and closer and closer and closer to 0. Okay, which means this gets closer and closer and closer and closer to infinity because the graph of natural log of x goes up. Oh, sorry, other way around. That would go up that way for our natural log of x. So this is actually infinity. And we know as x gets bigger and bigger in here, this number will get bigger and bigger and bigger and bigger and bigger. So that's over infinity. So we can actually use L'Hopital's rule now. Okay, so that means we have the natural log of y equals the limit as x approaches 0 from the right, the derivative of natural log sine of x divided by the derivative. Instead of 1 over x, I'll make it x to the negative 1 power. Okay, so you have the natural log of y is equal to the limit as x approaches 0 from the right. Natural log, put that over here. Remember, natural log of some g of x is equal to g prime of x over g of x. So this will be equal to cosine over sine. Divided by derivative of x to the negative 1 is equal to negative x to the negative 2, which is 1 over x squared. So that's negative 1 over x squared. Okay. So here, if we plug in 0, or the limit gets 0, this gets closer and closer to 1. This actually just gets closer and closer to 0. So if you have a number getting closer and closer to 1, divided by a number that's getting smaller and smaller and smaller, that's actually approaching infinity. Same thing here. If you have a number that's getting, well, a constant that's divided by a number that's getting smaller and smaller and smaller, then this is just getting bigger and bigger and bigger, but it's multiplied by a negative. So you have a really big number multiplied by negative 1, so that's times negative infinity. So we have to use L'Hopital's rule again. All right, so the thing about this one is you have cosine over sine. If you wanted to, you can just flip this and make it 1 over sine over cosine. So you can rewrite this as, and let me see if I can find somewhere to put that. I'm running out of room for notes here. Remember, cosine of x over sine of x is equals cotangent, which is 1 over tangent. So we can make this over tangent of x. And if we multiply our numerator and denominator by x squared, that will make that negative x squared up here. So we can kind of manipulate that a little bit to apply our L'Hopital's rule. So make sure. Okay, so that means we have the natural log of y, which is equal to the derivative of x squared over the derivative tangent of x. Oh, forgot my limit. X approaches 0 from the right. So limit x approaches 0 from the right. Here we go. So that's going to equal, I'm running out of room. And yeah, I'll go ahead and finish it up here. The limit as x approaches 0 from the right of 2x over derivative of tangent x, secant squared x. Okay. Which gives us, if we plug in 0, we get 0. We plug in 1, we get 1. So it's equal to 0, which is not our answer. This just lets us know, we'll continue this on the second page. It's almost done. This tells us that the natural log of y is equal to 0. Oh, anyone's still writing? I'll leave that up for now, for a few seconds. Actually, I'll just start writing underneath it. All right, so if we continue that here, that shows us that the natural log of y is equal to 0. So now we just apply e to both sides. So we have e to the natural log of y equals e to the 0. Remember, e and natural log cancel each other out. So you get y equals e to the 0, or y equals 1. And remember from the beginning, y is our limit of sine of x to the power of x. So this is our actual answer. Don't you hate it when you go through all that work and it's like a 1 at the end? Yeah, that just burns me up. Like, I went through all that for a 1. I could have guessed 1, but yep. So that's actually 1. Move this over a little bit. See like. All right. So any questions on that one? Right. So they can get a little bit lengthy. All right. So everybody, you just want to go, don't you? I really don't even ask. So if you have questions, feel free to ask. If not, I will make sure you signed in, and it should be floating around here somewhere. Oh, okay. Oh, so the sign-in sheet's on the back table.
Is anything like the natural log of e, is that all based on
Natural log is mostly in nature.
That's a really bad answer. For me, I don't know, I'll look it up. So I don't even know what it is. So that's like.
Oh, you're welcome. Have a good one.
Population growth or whatever is what the natural log is supposed to be. Where it came from.
I just have this progress report. I wrote down my Canvas grade in pencil. If you could just like sign it and then
Okay.
go over it in pen.
All right.
I know it.
Oh, okay. Oh, I think I got one. Hopefully it worked. Oh, thank you. It works. I'll put 0. I don't know. I mean,
I had one. I was sick.
take your word for it.
Can you just go over my my pencil and pen, just so that?
Oh, okay. Oh, I can go erase it. They may think it's kind of.
I don't want them to think I'm like.
Yeah.
Thank
There
you.
go. You're welcome.
not related to anything, but maybe just your honest opinion, because the advisors don't really know. So like, you said that you're not teaching Calc 2 next semester, but you are the following semester? Or you're not sure?
Not sure yet.
You're not sure?
Yeah. The only reason is because, and for some, and people always look at me funny when I say this, but these classes are Calc 1, Calc 2, those are really fun to teach.
Yeah.
Yeah. But
So
so
everybody
they
kinda-
disappear pretty quick.
Okay.
So
So.
me, I'm kind of like at the bottom as far as the hierarchy,
Mhm.
and so everybody else gets to pick theirs first, and these usually disappear fast.
Okay. So then like, the calculus-based physics that they teach here,
Mhm.
do you know much about it or no? Or know anybody that teaches it?
Mm,
Like, is it using most of what we learn in Calc 1? Or
I think
just,
with
they just
the-
want you to have Calc 1 done because you use it a couple times? Like,
I think with the
related
physics,
rates?
you don't have to know any of the proofs and anything. You just have to know how to find the derivative, what it's for,
Yeah.
stuff like that. Here, they don't really necessarily want you to go through all the steps and stuff in physics. They just want you to know, yeah,
it.
do you know how to find it?
Okay.
So,
Because I'm trying to see if it's worth, like, holding off on Calc 2 until the following semester.
Mm.
Or if it's just better to keep going. Like,
I would
guess I'm
keep
asking, is the
going.
calculus-based physics going to be enough of this that I would probably remember, I
Mm.
guess?
That I don't know.
Okay.
Can't say. But with this, I would, if possible, I wouldn't take a break because, and you'd be surprised how much you forget
Oh,
in
yeah.
like 3 to 6 months.
Yeah.
You'd come in like, okay, I know I did it, but a lot of it would just fade away.
Okay.
So it's best to
Better
take it like
just keep
one after
going.
another while it's fresh in your mind.
And then what's like a good teacher for Calc 2? Because not all teachers are created equal.
Mm,
Like, who would you recommend I try to get through?
so I haven't heard a whole lot of complaints about Professor Oaks.
Professor Oaks?
Yeah, Professor Oaks. I haven't heard too many complaints about him.
Okay.
I know that Professor Williams, I heard he's tough. So I'm not sure how they grade him as far as like how he relays the info.
Yeah.
But I heard he's a tough grader.
Okay.
So,
So
trying to think who
Williams
else.
I don't even know who the list of teachers are yet, but, all right.
Yeah, but I would definitely go. I would start with Oaks.
Start with Oaks?
Yeah.
Okay.
Don't forget your mom.
Think I forget that? I wanna know, like, you stalking me? You're like, hey, I know that dude in chemistry, I'm gonna find out where he sits at in math, just so I can be cool like that.
Same spot I do.
I know, that's kinda messed up.
Oh.
Yeah.